Brazilian zone. If we look at a sarcomere spans from a Z disk to a Z disk. And in the middle, if you will, or towards the middle of the sarcomere is where the thick filament is. Right? And then towards the ends, or lateral, if you will, on the sarcomere is where the thin filament is. And then there's always a little area where thick and thin filaments overlap. There must be, right? Because if they didn't overlap with each other, they couldn't interact with each other. So in essence, I mean, if you were to stretch a sarcomere so far that actin and myosin no longer overlap, guess what you just did? You ruined the sarcomere, right? It can't contract. So we have these stabilizing proteins built in to prevent that overstretching of the sarcomere. Things like titin here, you'll see how it's going to help prevent overstretching. And nebulin here, which helps stabilize actin. This is a very big protein here, actually. By big, I mean heavy. Number of daltons, I can't remember, but it's one of the largest in the body. So where the interaction occurs, where power stroke cycling occurs, is right here, at this interaction between actin and myosin. We labeled in anatomy these different regions. When a muscle contracts, what happens is Z discs approach each other. This area in the middle gets shorter, right? So the H zone here in the middle decreases. As that happens, this gets closer to this, right? So the I band gets shorter also. The A band always stays the same length because it's defined by the length of the myosin. And in fact, that's how they figured out that the filaments slide past each other rather than shortening themselves. Because the A band stayed the same length, that implies that myosin doesn't shorten, right? And because the I bands, the I bands got shorter and the H zone got shorter, that implied that actin was moving over the top of the myosin. So they figured that out, this kind of interaction part back in the 20s and 30s, about just by seeing what happens when a muscle contracts. Okay? And then subsequently, when they got better ability to study, they could actually look at the interactions between actin and myosin. Okay? Now what's interesting about myosin is that myosin is both a globular, or has a globular component to it, and a filamentous component to it. And the globular component is the head, and that's what's allosteric. So if you look at myosin here, and we look at it, there's a filamentous part of it here coming out, but then it's got this head, like this, that sticks up. And that head is what is allosteric. So if we draw it like this here, okay, it can look like that, and if we look at that like that, we actually have the head at a 90-degree angle relative to the tail here, or this linker. Okay? And so that's one form of the myosin head. The other form of the myosin head is this one. Where it has a 45-degree angle to that linker, like that. I didn't draw it to scale, but you see how it swivels, right? So this myosin head can swivel right here. Okay. Now what's interesting is that this form of it right here is a high energy form. This form of it right here is a lower energy. Now, what do you know about systems and energy is that they always want to tend towards a state that takes the least energy to maintain, right? So myosin wants to be in which way? This way. Myosin would prefer to just be like that. But I can force it this way if I add what? If I add energy. So going this way here is endergonic. I have to add energy, right? Going this way here is exergonic. This releases energy. You okay with that? So if we're at high energy here and I let it swivel, it's going to release energy. If I want to put it back to the high energy state, I have to add energy. So exergonic this way, endergonic this way. What's my source of energy? ATP. So now look at this. This is important. ATP is used to push the head back to 90. ATP is not used to swivel it down to 45. It's used to push it back to 90. When it goes from 90 to 45, it releases energy. And you can use this energy to do work. In fact, what you're going to use it to do is to pull on actin. Okay? So ATP puts energy into myosin. Myosin, now we've got potential energy in the form of this head of myosin. Then we use that energy in the head of myosin to pull on actin. You okay with that? So, and when you pull on actin, what happens to the Z lines? They get closer together and the sarcomere shortens. Now this is important because is ATP used direct, and by the way, this is called the power stroke when that happens. Is ATP used directly to pull on actin? No. Myosin provided the energy. ATP is used indirectly. Okay. It's used indirectly to restore. Okay. So this back and forth here, 90, 45, 90, 45, 90, 45, 90, 45. This is called the power stroke cycle. When it pulls on actin, that is the power stroke. Okay. You okay with that?